Hello everyone, welcome back to online lecture series on applied thermodynamics. We are continuing our topic of reciprocating compressors. So, we will first revise our previous topics and then we will begin our new topic. So, reciprocating compressors are mainly used for compressing the air, and this compression is typically done in a piston cylinder arrangement. Now, the reciprocating compressor can be in form of single or multi-cylinder arrangement. It can be a single acting or double acting, and it can be a single stage or multi-stage. Hopefully, today we will be discussing about how multi-stage compression works. A single cylinder, single acting reciprocating compressor has a pressure ratio of typical values 5 to 8 at 100 to 1500 rpms, and these reciprocating compressors are generally or obviously a work consuming device, so they are driven by electric motors or IC engines. So this is the arrangement that we have seen in our previous lecture, that it consists of suction valve and delivery valve, and the rest of the components are very common to IC engine, where we are having piston rings, water jacket, piston cylinder, connecting rod, a flywheel, crank and crankshaft. So these are the common components similar to IC engines, and we discussed about two important strokes, that is suction stroke and delivery stroke. It's all about the pressure difference between the atmosphere and inside the cylinder, which enables or disables the valves. And we have already discussed this, so we are not going to repeat the same. And then we were about to discuss the working of reciprocating compressors. So for that purpose we have PV diagram and TS diagram. As you can see, a typical reciprocating compression consists of three processes. First is suction, as you can see here, then the compression process, and then the discharge process. For the main process, that is compression over here, it can be done in three different ways. It can be an isothermal, a polytropic, or an adiabatic, and the same can be seen over here also. So this is the PV and TS diagram that is already done, and now we will derive the formula for work requirements by a reciprocating compressor, considering all three kinds of processes, that is namely isothermal, polytropic and adiabatic. So let's begin this work. So what we are going to do here is we will first copy this into our virtual board, that is Paint 3D over here. So I hope it will be very much visible to you. And now let's begin with our derivation part. So first we will be focusing for an isentropic process. See, we are not going to use TS diagram as of now. If it is required, then we will bring it back from the presentation. So our goal is to obtain the work done. So work done is equal to area under one, two, three, 4 and 1. So as you can see, if I need to show you in this way, then here it should be this much of area. You need to be very careful on this. So we are looking to calculate this much of area. Okay. So this will be the work requirement by a reciprocating compressor in case of isentropic compression process. So this is the area we are going to calculate, and now the task is how we can calculate this. So let's do this here. Area okay, what we are going to do here, we are going to add few nomenclature here. Let's say this point to be A, this point to be B, and this point to be C. So we haven't done this in our previous lecture. So first let's see how we can calculate this. So area under 2, 3, A, B and 2. So what we are doing actually is this is what kind of area is this? This is actually a rectangular area, that is this. So I again tell you that you need to be very careful while I am making this work done derivation. So this much will be the area. So this rectangle, see, I also told you that here it is P2 pressure. So this will be, the whole area will be P2 V2. So still this is not the area that we desire, so we need to continue here plus. So first let me erase this area part. Okay, so here we have this as P2. Let me repeat this. So this will be equal to P2 V2 plus area one, 2, B, C, 1. So what kind of area is this? This is only this much of area. So consider this to be a vertical line like this. So this will be the area we are going to calculate. Okay, so this is actually based on the isentropic work, so it will be like this: plus P2 V2 minus P1 V1 divided by gamma minus 1. See, we have done this formula in our fundamental thermodynamics, so we are not going into details that how we have obtained this equation. Next, then what we are going to do is minus area one 4 AC. Oops, we went so down. So here AC 1. So which area is this? Let's focus here. So that area is this. Minus P1 V1. So okay, let me again explain you how we have arrived up to this minus P1 V1. So our objective is to obtain this much of area: 1 2 3 4. Okay, we are looking for this area. So what we have done here, that we have first, just wait, this is the area that we have first taken, that is 3A 2 V. Then we took another area, that is this 1 2 and then this, that is 1A 4 and C. So if you see, this is, if we make a small mathematical relationship, then this plus this minus this. So what I would suggest you, that if you take this entire figure in a single frame, then you will be able to understand this formula. Okay, so you can pause this video and go through this by yourself, that what I have done here. I have added this to and subtracted this small rectangle of the bottom. Now let's focus over here. We have spent enough time on that. So E is equal to E2 V2 minus P1 V1 plus P2 V2 minus P1 V1 divided by gamma minus 1. So what we will be getting over here is, we will not go into small details right now. So we are getting finally is equal to gamma upon gamma minus 1 V2 minus P1 V1, and this will be the work done W. And what else we can do over here? Is gamma upon gamma minus 1. We can write down m r t2 minus m r t1 is equal to, we can say here that gamma upon gamma minus 1 m r t2 minus t1 w. So what we will do here, we will still continue from our previous equation, that is this equation. So here W is equal to gamma upon gamma minus 1, and here P1 V1 is taken common, so P2 V2 divided by P1 V1 minus 1. Now we will have some other work besides this, that is, as we are discussing about an isentropic process, so we have a standard relationship P2 V2 raised to gamma is equal to P1 V1 raised to gamma. So we can say that here V2 divided by V1 raised to gamma is equal to P1 upon P2. So V2 upon V1 is equal to P1 upon P2 1 over gamma. And we can further write down V2 upon V1 is equal to P2 upon P1 raised to minus 1 upon gamma. So that is the equation of our use or of our interest. So let's continue this. Is equal to gamma upon gamma minus 1 P1 V1 P2 upon P1 into P2 upon P1 raised to minus 1 over gamma minus 1. So let's continue from here. Is equal to gamma minus 1 P1 V1 P2 by P1 so gamma minus 1 over gamma minus 1. And if we see, this will be joule per second per cycle. And we can further modify this will be W. So further we can write down W as equal to gamma upon gamma minus 1 m r T1 P2 upon P1 gamma minus 1 over gamma minus 1. So we have written this in temperature form, nothing else. So the unit will remain same. So these are the equations, and we can further modify this by writing it in independent of mass, that is R P2 by P1 raised to gamma minus 1 over gamma minus 1 joule per second per kg of air. Okay, so this will be the W. So these are three important relationships that are important. These are final relationships that we are having for polytropic, so for isentropic process. Okay, even we can further reduce, so that is fine. Now what we are going to do is we will have the second case. Okay, let's first copy this work into our main slides. So now as you see, we have done this for isentropic process. Now we will write down the same equations for polytropic process. So second case is polytropic process. So in polytropic process, the only difference is the adiabatic index or isentropic index is replaced with the polytropic index. So instead of gamma, we will be writing down the n. So let me erase few things over here. So these two we will be keeping. So let me erase this. here it will be n minus 1 upon n, here n minus 1 upon n, n upon n minus 1 and n upon n minus 1, and one other we can write down is n upon p1 v1 minus p2 v2. So we are not deriving this because it will be exactly similar to the isentropic process. Now we will move forward with our third derivation over here, that is for isothermal process. So the process will remain same over here. The only thing that for isothermal will change is the 2 will be replaced by 2 double prime. Okay, so let's erase this. Double prime. So we can say, I think we will again require this service of this figure, so let's copy this over here. So this is like, let's say over here is equal to area to double prime 3, that is the big rectangle, plus area 1 2 double prime 3. Okay, we will keep it up to this. Now we will not repeat the entire words. Minus area 1 4 or 4 1. So here what we will be getting is, this will be again p1 v1 plus p1 v1 v1 ln v1 upon v2 minus p2 v2. So here area under 4 1, I think we have done the reverse thing. Here it should be p2 v2 and here it should be p1 v1, and as you know, for isothermal process these two are equal, so these two will get vanished, that is p2 v2 and p1 v1 will go. So we are left with is equal to p1 v1 ln v1 upon v2, or we can write down this as equal to p1 v1 ln r p2 by p1, and we can write down is equal to m r p1 ln p2 by P1 joule per second per cycle, and here we can write down further is equal to R P1 ln P2 upon P1 joule per cycle per kg of air. Okay, so let's copy this work into our main slides. We are done with the derivation part. So let's first copy this. So with this, that is the end of today's lecture. Thank you for watching this video.